Hi friends, so in this lecture we will continue from our dynamic programming part 1 where we saw what is dynamic programming and why it is useful. So let us see these two codes, one of which is more efficient and one is less efficient. So this one is using dynamic programming and this one is using plain recursion and no dynamic programming in it. So both are solving the Fibonacci number problem. So this is how this one is solving. Let's see. So this is a function fn. So if we are getting to the base case, we return 1, else we return the sum of two previous numbers. Okay, so we are returning f, let's say we call f3, so it is calling f2 and f1, so f2 gets computed. Okay, but let's say my parent was f5, so it has also called f4, which will also called f3 and f2, so there also f2 is being called. So again those computations are taking place. But let's see this one. This is the iterative version of the same problem. So what we do is we take an array f6 of size 6, f0 and f1 are initialized to 1, and for I is equal to 2, I less than equal to 5, I plus plus, what we do is fi is equal to fi minus 1 plus fi plus minus 2. So we are calculating in this order. So f0 and f1 are used to compute f2, then this one and this stored value are used to compute f3. So f2 is just computed once, f3 is just computed once, f2 and f3 are used to compute f4. Everything is computed once. f3 and f4 will be used to compute f5. But I think you clearly understood what is the difference between these two versions. This function version, then each time as we saw in this recursion tree, f2 is required 3 times in this problem according to this recursion tree. So this f2 method will be called 3 times, and each time it will be recomputed freshly. So this affects our efficiency and this makes this less efficient. This plain recursive approach is less efficient than our dynamic programming approach. So dynamic programming is quite useful, and the code complexity looks almost the same. These are 3-4 lines code. This is also a 3-4 line code. So this is a very simple program dot. So designing an iterative solution was as simple and intuitive as designing a recursive solution. But generally, if a formula that is the recursive formula for a dynamic programming problem, if it gets too complex and we don't have much time to think, okay, so there is some time constraint, means you just want to quickly solve the problem, we might just want to write a recursive function which contains 2-3 lines of base cases and 1 line of the recursive formula. That's all. So this is what we saw here. This is the 2 base cases we handled here, and this is the formula we write here, and rest everything will be taken care in the recursion. So recursion takes care after that. But in the recursion tree, how to not solve the sub problems again and again? Okay, so here we saw that in this recursion tree, f2 is called 3 times, and each time it is freshly recomputed. So how to avoid that part? So recursion tree follows first order traversal for computation. That is, step 1, my left child returns me a value. Let us see here what these steps mean. Step 1, let's say we want to compute f5. So my left child, that is f4, will return me a value. Step 2, I call my right child and my right child returns me a value. So f3 will return me a value. Then I do something. Here what is that something? We are adding those two values which are returned by my children. Maybe add like in the above problem and return to my parent if it is there. If it is root, then the problem ends. Okay. So this was a quite simple example. In general, the recursion may not be binary. That is this is the note. Here only 2 children per parent, but there may be more children, 3-4 children also. Okay. So this is just a simple point. So one of the f2 is computed. Let's see this problem. f4, f3. So this is divided here. So this is computed first, this is computed second, and when both return to their parent, then f4 is computed, gets computed. So first this one is computed, then second is this one is computed. What we will do in a typical normal recursion, but we want to do something else. As soon as we compute it, we store it in, say, a global array. So here we first compute it. f2 is first computed here because we follow the post order traversal. So this f2 is computed before this one using the post order traversal of this recursion tree. So when at the instant when f2 is first computed, the first instant of time when f2 was computed, we just store it somewhere, maybe in a global array. Why global? Because recursive functions are different and they will have different copies of their own variables. So the global variable will be shared by all those recursive functions which are called again and again, because each depth a new instance of function is called. So this global array, which is initialized by all -1, before computing f2 for the next time, we just check that array. The array is second index. If it is -1, we need to compute it. So sad. That is, if f of 2 is -1, that is still not populated, we need to populate it. But if it is not -1 and there is some value already there, then we can use just use that value, and we are saved off all the effort. So let's look at the code. Okay, so we create a global array which I am calling hf, that is helper of f of size 10, and for I is equal to 0, I less than 10, I initialize to -1, and hf0 and hf1 I am initializing to 1. Okay, and this is the simple plain recursive function. I have just added this hf in this function. So this is as simple as writing a simple plain recursive function, but with the added benefit that it is using dynamic programming and computing each subproblem only once. So overlapping subproblems are computed only once. So if hfi is -1, then we need to compute hfi as f of I -1 plus f of I -2. I need to call my children to compute it. There is no other way. hfi doesn't know the value because it is -1 yet. So there is only one way. I need to call my children, and as I call my children, I just populate hfi because now I know the value of hfi, and then I return hfi. So if hfi is not -1, then this step is bypassed. I just return hfi. If hfi is not -1 and it is having some useful value which is populated by some function which was called before me, then I am having a useful value in hfi and I am just returning that value. This step is bypassed in that case. So this step will not be executed in that case. if HF is having some useful value. So only this step. So no children are called, no nothing is called. So at this point HFI is not populated. I need to call my children, compute the sum and populate the HF2 with value of whatever I get, and then I return to my parent, and then I sit here. When the control comes here, then it checks HF2. Hey, it is not -1, it is having some useful value which is pre-filled by some previous F2, so I can use that. So this code, I think you understood this code. So this technique is called memoization. That is, F2, once it is called, it is memorized, and this is plain recursion and quite simple to write, but yet it is solving the overlapping subproblems once only. So let's quickly look at how our original problem of Boolean parenthesization follow these two properties. First property is optimal substructure. It is clear because optimal solution of subproblems are actually being used to form the solution to the given problem, because I to j we are separating in two parts, I to k and k plus 1 to j. So optimal substructure is clear, and they are leading to the optimal solution of this problem. This is also clear. So now let us look at how subproblems are overlapping. So let us take a simple example, T1 to 4. So it is divided into T1 1, T2 4, T1 2, T3 4, and this is further divided into this and this. So these two subproblems which are overlapping can be observed, which is T3 4. It is repeating to more, and similarly more repeating cases can also be found in this recursion tree. So in this way you can observe these repeating cases, and this is also following the overlapping subproblems property. So this is satisfying the two properties required to be satisfied to be solvable by a dynamic programming approach. Hence this problem can be solved successfully by a dynamic programming approach. Thank you, friends.